welcome to another episode of Ask a Physicist, on a very explosive topic, if you will. Rabanda120055 asks, could you talk about nuclear and atomic bombs? And the answer is yes. In fact, I'm very happy to. Not only because there's very interesting physics in this topic, but also because, well, nuclear weapons have played quite a significant role in the history of the world. For example, in the unfortunate events in Hiroshima and Nagasaki during the Second World War, and also play a major role in politics today, which is unsurprising, seeing that 1 ton worth of nuclear weapons produces an equivalent amount of energy as 6 million tons of TNT. So yes, I'm very happy to talk about this topic. But well, before we get to the exciting part, let's start by clarifying what we mean by nuclear when we talk about nuclear weapons. As I've mentioned before, every piece of matter you've ever seen consists of atoms. Billions of them. And every atom consists of electrons on the outside and a nucleus on the inside. The core of the atom, if you will. Now this nucleus consists of what we call nucleons. And these can be either protons or neutrons. Now, a nuclear reaction is a reaction in which the number of nucleons in the atom changes. And these are, in fact, exact sort of reactions which allow nuclear weapons to work. It is very much like in chemistry, where we take a number of things, put them together at a given temperature, and get new things out, plus a bit of energy. The difference is that in physics, we actually know where that energy comes from. And, as ever so often in physics, it brings us back to Einstein and his famous formula E=mc². Now, what this formula means is that mass, the thing you weigh on a scale, and energy, that is heat, kinetic energy or radiation, are interchangeable. That means if you converted a given amount of mass into energy, you'd find out how much mass it is, and you times it by c, which is the speed of light, squared. That means even a small amount of mass can produce a very large amount of energy. Now, the funny thing about nuclei is that if you take a given nucleus, you weigh it, and then rip it apart into its different nucleons, and then weigh those again as separate entities, you will find that the nucleons weighted separately have a greater mass than the nucleus itself. So we see that when taking a given nucleus apart, we somehow gain mass. And vice versa, if we put given nucleons into a given nucleus, we somehow lose mass. Now, this mass isn't just lost, but as we know from Einstein's formula, is in fact converted into energy. And this is actually the energy we get out in nuclear reactions. Now, all of you are probably wondering, how is this possible? How can it be that arranging nucleons in a nucleus changes their mass? Well, to explain why, I have to introduce you to a new force in nature, which is the strong, or also called the nuclear force. Now, if you remember from a previous video of mine, I've talked about the electromagnetic force, which attracts oppositely charged particles, such as protons and electrons together, and repels particles with the same charge. Now, the strong force is quite different from that, as in it doesn't care about the charge of a particle and instead only acts on nucleons and attracts them together, no matter what. Now, the reason we call it the strong force is that on a nuclear level it is much, much stronger than the electromagnetic force. In fact, if you bring two nucleons close enough together, they will attract each other through the strong force, and the electromagnetic force becomes almost negligible. Now the question is, what happens when you pull two particles which strongly attract each other apart? Now the principle is similar to what happens when you try pulling apart a rubber band. As you pulling it apart, you start storing up in it potential energy, as we call it. We know this because when you let it go, it will shoot together again, and you might even hurt your fingers. That is the rubber band converting potential energy into kinetic energy. But that's not the point. The point here is that the particles which are being pulled apart store up potential energy. And as we know from Einstein's E = mc squared, energy and mass are interchangeable. So in actual fact, pulling particles apart increases the overall mass of the system. Vice versa, putting particles that attract each other together decreases the overall mass of the system, because you're reducing the amount of potential energy. And this is actually the energy we get out in nuclear reactions. Now, this explains why combining different nucleons into one nucleus causes energy to be released. More importantly, it shows that merging smaller nuclei into bigger nuclei also can release energy. For example, in stars like our Sun, hydrogen nuclei are merged into helium nuclei, and eventually helium nuclei are merged into carbon and oxygen nuclei. These processes all release energy, which fuels these stars. Now, processes where nuclei are merged are called nuclear fusion. However, what you have to take into consideration here is that the amount of energy you get out of a given nuclear fusion process depends on how tightly the nucleons are bound in the initial and the final state. When you're fusing hydrogen to helium, or when you're fusing up from helium to carbon, you're making a very significant change, as at first, in helium for instance, most of the nucleons are essentially part of the surface of the nucleus, while in the carbon nucleus, many of them will be completely bound on all sides, i.e. the binding that each nucleon experiences is much greater in the carbon atom. In other words, there's a great change in potential energy in this fusion process, and thus a lot of energy will be released. However, when you fuse carbon into bigger nuclei, the change in binding of each nucleon in the nucleus will be much less, and as a result, the energy per nucleon we can gain from fusing nuclei together decreases as we get to bigger and bigger nuclei. Also, another fact that we need to take into account is that as the nuclei get bigger and bigger, they contain more and more protons. And as you know, protons repel each other, which actually counteracts the attraction from due to the strong force between the nucleons. And once this effect becomes significant enough, the energy that can be released from fusing nuclei together actually becomes zero. For even bigger nuclei, the energy actually becomes negative. In other words, at this point, we can actually release energy by splitting the nuclei apart. This process is called nuclear fission, and it's the principle upon which the first nuclear weapons were based. And I'm getting to those right now. Tons of TNT. So yes, I'm very happy to talk about this topic. But well, before we get to the exciting part, let's start by clarifying what we mean by nuclear explosive topic, if you will. Rabanda120055 asks, could you talk about nuclear and atomic bombs? And the answer is yes. In fact, I'm very happy to. Not only because there's Hello everyone, and welcome to another episode of Ask a Physicist. On a very Second World War, and also play a major role in politics today, which is unsurprising, seeing that 1 ton worth of nuclear weapons produces an equivalent amount of energy as 6 million. Very interesting physics in this topic, but also because, well, nuclear weapons have played quite a significant role in the history of the world. For example, in the unfortunate events in Hiroshima and Nagasaki